volumes and venoconstriction. Okay, now, so that's volume. How much blood is in the different sections. Now we got to talk about the characteristic of the pipes involved. Okay, so one of those characteristics is cross-sectional area. All that, it's a big complicated term, but all that means is how big is the pipe, right? In other words, if you, like the aorta, we'll just use these examples. 2.5 centimeters squared, so it's a very small structure. Have you seen the aorta yet? Have you cracked the chest? No, okay. So it's a relatively small vessel. Well, what about the small arteries? Okay, here what we've done is this isn't the cross-sectional area of one small artery. Okay, one small artery would be much smaller than the aorta. But you don't just have one small artery. You have a whole bunch of small arteries, right? So think about the aorta. The aorta branches. Each branch also has a cross-sectional area. So as we go towards the capillaries, the amount of the size of the pipe overall gets bigger. All right, let's talk about rivers for a minute. Because I think that makes this easier to understand. Okay, so you have, here's a river, right? And you've got blood flowing, or not blood, you've got water flowing in the river, right? Okay, so this river, if we were to look at the river from the side, okay, let's say that it looks like that, and here's the surface of the river. Okay, so we have a cross-sectional area that's passing through, that this water is passing through. All right, now let's say that our river enters a big, wide valley, and it spreads out, right? So here's our river. Now here, if we were to look at the river from the side, it would look like this, right? So we've taken, so the same amount of water passing through here is passing through here, right? Because we don't have a dam or anything. But because the cross-sectional area is different, the water here will be running slower or faster than the water here, for those of you who have been in a boat. What? Slower, much slower, right? The narrower the canyon that the river goes through, the faster the water goes through it. Well, the same thing is happening in our vessels, okay? The aorta is the canyon. As the aorta branches and branches and branches, we get a wider and wider riverbed, which means that the fastest blood is going through the aorta. As we go to the smaller tributaries, the flow gets slower and slower and slower until the river starts to come together again, right? So aorta breaks into small arteries into arterioles, arterioles into capillaries. The capillaries are the big Mississippi, right? Moving huge amounts of fluid, but moving it very slowly. Now we take the Mississippi and we start corralling it into smaller channels, right? So venules, and then small veins, and then vena cava. So it means by the time we get to here, is blood moving faster or slower than at the capillaries? Faster again, right? So blood starts moving fast. It gets slower and slower as its cross-sectional area increases. Then as it comes back together, it speeds back up again. Now, thinking about the physics of it, is the speed here in vena cava ever going to be faster than the speed in the aorta? No, because of resistance, right? Some of the energy has been lost. Now, the other reason is 8 is bigger than 2.5, too, right? So you never get all the blood back into the same amount of cross-sectional area. And that's because we have two vena cava. We have a top one and a bottom one. All right, so cross-sectional area, how much pipe is the blood going through, changes as we go out through the circulation. Okay, so the speed changes. So fast blood flow in the aorta, slow blood flow in the capillaries, faster blood flow again in the vena cava. Okay, so we've looked at volume. we've looked at cross-sectional area. Now let's look at pressure. So graph, right? So here along the x-axis is moving through the circulation, right? From left atrium all the way to the pulmonary side, and then from pulmonary side back to the left atrium. What we see on the y-axis is pressure, all right? So in the left atrium, here we see a very low pressure, okay, because blood, remember, trickles back to the heart. And then we see very small little bumps. That's atrial contraction. Told you it was pathetic, right? Nothing much, right? Little tiny bits of contraction. All right, now from left atrium, next area, left ventricle. So now we're on the other side of the AV valve, okay? Now inside the ventricle, as we talked about from the big graph the other day, we have huge pressure swings, right? We go from left atrial pressure all the way up to systolic blood pressure and then back down. Why the big pressure changes? Because that's the heart's job, right? Its job is to pressurize the blood. So it's doing its job. It's pressurizing and then ejecting, right? So if we were to measure pressure in the ventricle, big swings. All right, next stop, aorta. Here, it's all on the high pressure side. We have systolic at the top. Bottom is diastolic. Very good. That's the other side of the pressure, right? Diastolic pressure. And what keeps that pressure high is, of course, the aortic valve, right? The aortic valve closes when pressure in the aorta becomes greater than pressure in the ventricle. So what that means is that the aorta is able to hold on to the heart's pressure even as the heart relaxes then, right? So we have high pressure in the aorta, systolic, diastolic, systolic, diastolic. Okay, now our aorta starts to branch. Now we're into your anatomy, right? So the aorta branches and branches, and we see the pattern, large arteries, small arteries, arterioles. Okay, we still see big swings between systolic and diastolic, systolic and diastolic. We even see, if you look really carefully, there's actually a subtle increase in systolic pressure. The pressure in your brachial artery is actually a touch higher than the pressure in your aorta. That has to do with elasticity, how springy the vessels are. We're not going to talk about that for right now, but just explaining that little upstroke. Okay, so large arteries, systolic, diastolic. Now, as we move to the small arteries and arterioles, though, you can see that even though we have pulsatile flow, high pressure and low pressure, the mean pressure is decreasing as we head towards the capillaries. Okay, why? It has to do with branching. We're taking the same amount of pressure and we're putting it into more and more vessels, more and more cross-sectional area to be specific. So we see a reduction in pressure because we're spreading that pressure out over a wider number of vessels. So as we get to the arterioles, okay, we still have relatively high pressure compared to the left atrium. It still is pulsatile. When we leave the arterioles, though, you notice the pulsations end, right? Capillaries have very smooth blood flow. It doesn't stop and start, okay? And the arterioles are sort of the end of pulsatile blood flow. They don't make it stop, but they're the last vessels where you really see it matter. What makes capillary blood flow so smooth is that they're so tiny, okay, that the red cells have to sort of squeeze through. That becomes the limit on how fast they can go, not what the pressure up and down is from the heart. So we can see in the capillary beds, the pressure is flat and still decreasing. Now, a key point I want you to see here, the pressure in the capillaries obviously is much less than the pressure in the aorta or the large arteries. That, I think, is intuitive. But note that the pressure in the capillaries is still higher than the pressure in the veins and in the right atrium. Okay? What returns blood flow to the heart is pressure. So the only way you get blood from your capillaries to your heart is the pressure in the capillaries has to be higher than the pressure in your heart is. Otherwise, there's no way for it to get back. So that means the area in the body with the lowest pressure is the right atrium. Okay? Veins next, then capillaries, then arterioles. That's going backwards, right? Because in the end, the pressure in the capillaries must be lower than the pressure in the right atrium, or the blood won't get back there. Because there's only one pump in the system, and that's the heart on the other end. All right, so capillaries, constant pressure, non-pulsatile flow. From there, we go into veins, okay? And you don't see a lot of pressure change, but the venous pressure is lower than the capillary pressure. The right atrial pressure is lower yet than the venous pressure. Okay, so now we're in the right atrium. Right atrial pressures go up and down a little bit. That's right atrial contraction. Again, pathetic compared to the ventricles, right? Here's our right ventricle. Contraction, relaxation, systole, diastole. You'll note that the right ventricular pressure is quite a bit smaller than the left. Okay? The pulmonary circulation is low pressure, has a much lower pressure and a much lower resistance than the systemic circulation does. Translation, the right side of the heart has much less work to do than the left side of the heart does. The pressures are lower, the distances are shorter, and the resistance is lower. It's one of the reasons why the right ventricle is thinner. Like if you look at the walls of the right ventricle, they're quite a bit thinner. All right, so same pattern, just lower pressures. Big swings in the right ventricle, systolic down to 0, systolic down to 0. Pulmonary arteries, okay, we see the same pattern as we do in the aorta, right? So we have pulmonary systolic and then pulmonary arterial pressure. Same arterioles, capillaries, venules, veins, same pattern, lower pressure. Okay, so so blood returns to the left atrium. Now, the pressure in the right atrium versus pressure in the left atrium. The place of lowest pressure on the systemic circulation is right atrium, right? Because that's the end of the systemic circulation. If you look carefully, you'll see the pressure in the right atrium is slightly higher than the left atrium, and that allows blood to continue its journey back to the left atrium before it goes again. But effectively, left and right atrium are very close to 0. Okay, the difference between the two pressures only comes up really in cardiology and ICU medicine.